Let me find it right quick. So I want to point out something on the periodic table real quick. And this, while we're talking about isotopes, and we don't have to go into a whole like lecture on isotopes. I just want to show you how they can be expressed. And then we're going to move on to calculating percent abundance and things like that. Why is my browser not coming up? Everything has been dragging today. I'm not sure why. It's coming. At some point it'll come up. Oh, come on. All right. So let me go back to to here. All right, so let's take boron. Let's take boron. So boron, if you recall from the other day, we talked about boron and we talked about we talked about the periodic table and talked about what the numbers mean. So 5 is the atomic number. That means it has 5 protons. And if it's neutral, that means it has 5 electrons. But down here, this is the atomic mass. But sometimes when you see the isotopes represented, you'll see this written differently. So you'll see boron written with the atomic mass in a superscript and the atomic number in a subscript, right? So there are 2 known isotopes of boron, boron 11 and boron 10. And so when you write the isotope out, I'll show you in a second on the page on my iPad. You'll write the atomic mass up top and the atomic number below it. And I'm just saying that because we're going to see some examples where we have the isotopes expressed that way. And so with any one of these, like let me go to magnesium, right? Magnesium has an atomic number of 12, meaning there are 12 protons and 12 electrons in a neutral species, and an atomic mass of 24. So magnesium actually has 3 different isotopes. It's magnesium 24, 25, and 26. So here, if you wrote this in isotope form, the atomic mass would be up top, and then the atomic number would be here. One thing that's not going to change, the atomic number itself is not going to change, but the atomic mass can change. That's how we distinguish between isotopes. So let me show you. Here, share my screen. Hopefully it won't take forever like it did for my last class. Today is the 9th. Right, so if I were to write out the isotopic depiction of magnesium, I would write it like this. So magnesium, the 12 will go here, and then the 24 up top. So again, this is atomic mass. This is atomic number. Right, and then if I wrote the isotope of magnesium 25, that would be here, 25, and then 12. The 12 is not going to change because the number of protons doesn't change in an isotope. What changes in an isotope? Anybody? How do I go from 24 to 25?
The change of electron numbers.
Not the electrons, because the electrons are too light. Like they don't have enough mass to change the atomic mass. What's the other particle? You got electrons, protons.
Protons and neutrons. So if you change the number of protons and neutrons in the nucleus.
Yeah, you're changing the number of neutrons. The protons never change. Right? Protons stay constant. The electrons can change, and the neutrons can change. So for an isotope of 25, that's going to have an extra neutron in the nucleus. And then magnesium 26, we'll write it like this. Notice the 12 is the same in all of them, right? So that number won't change because the protons don't change, but the neutrons can change and the electrons can change. And again, the top number, when you see it written like this, the top number is the atomic mass. The bottom number is the atomic number. All right. So with that being said, when we talk about atomic mass, right, that number that we see on the periodic table is really an average, right? So the atomic mass, again, is based on the number of protons and neutrons. That's what Z is based on. Remember, that's the symbol for atomic mass, Z. And what the number you see on the periodic table is actually the average. So the periodic table Z value is an average. And this is important, right? It's an average of all naturally occurring isotopes. The naturally occurring part is really important, right? So if it occurs in nature, no matter the percentage, even if it's a very, and a lot of times some of the isotopes will have very small percentages that are different from like the main isotope or the main element that exists. But if it's naturally occurring, then what you see represented on a periodic table is actually an average. We call it the average atomic mass. Right, and there's a way to calculate that. Right, it is the sum of the isotope fraction. In other words, what percentage of this element is this isotope? Like if we go back over here to magnesium, these are all, they all exist in different percentages, right? So magnesium 26 has a specific percentage that it exists in naturally. 25 and 24 have percentages, but all the percentages have to add up to 100. So the isotope fraction is the abundance, what percentage, and that is multiplied by the mass. Shrink that down. All right. So it's a sum of the fraction times the mass. So if you have 10 fractions, right, 10 different isotopes, you'll do this. It'll be like the abundance times the mass plus the abundance times the mass of the other one plus the abundance times the mass of the other. So that's how you get this average average mass, right? So let's do an example right quick. So let's take boron. We just talked about boron and said that it has it can be B11. And let me get, I think it's 5. Let me go back and make sure I got Yes, 5. So B11 or B10. Now, let me ask this question based on something we talked about on Monday. If it's B11 and the atomic number is 5 and the atomic mass is 11, how many neutrons does it have in the nucleus? How do we determine that?
Would it have 6 neutrons?
6 neutrons. Good. The way we determine it is a quick way to remember this is the alphabet. So we go A minus Z. A is the mass. Z is the atomic number. If you subtract them, that gives you the number of neutrons. Right? So for B11, this isotope, it has 6 neutrons. What about B10?
Would it be 5?
5 neutrons. Excellent. All right. But that's just to keep you on your toes about how to use these numbers to distinguish different things. But let's go back to the question. So now we're talking about how to calculate the average mass. So if B11 has an abundance of 19.9%, I'm sorry, 80.1%, my bad. B11 has an 80.1% abundance. And then B10, again, atomic mass on the top, atomic number on the bottom, has a 19.9% abundance. We can calculate the average mass from that. All we do is take, again, the fraction times the atomic mass of the isotope. And we're going to add those two together. Right? So the average mass for boron, we would calculate by taking, and we want to take that percentage and turn it into a fraction. So we'll say 0.801. You know, when you're working with percentages, all you have to do is divide the number by 100 and you can get the fraction. So 0.801 multiplied by 11 plus 0.199 times 10. Right? This is the 11 is for the boron 11 isotope. The 10 is for the boron 10 isotope. All right. And remember, if we're taking the average, it's the sum of the isotope fraction times the mass for all of your isotopes. All right. Can somebody calculate those real quick? And let me give you, before you calculate it, let me give you the exact number. This is 11.0093, and this is 10.0129. And it's in atomic mass units. So that's what those are the numbers that you'll use to calculate those more precise numbers times the fraction. Anybody got it yet? Go ahead, Amaya.
I'm calculating right now, but I also had a question.
Go ahead.
Why did you the AMU 11.0093 and the
Mhm.
10.0129?
Mhm.
Where did those come from?
So those are the precise masses of the isotopes.
Oh, like it'll be like given to us.
Yes, of course.
Oh, okay, okay,
Absolutely.
okay. And I got 10.811. I don't. Did you want me to do sig figs or?
That's all right. We'll
Okay.
take it. So 10.81.
8110.164.
All right. So yeah, let's make it 4 sig figs
Okay.
and keep it like the periodic table, because I think they report everything in 4 sig figs. All right, so we'll leave it there. So 10.81 is the average mass. What number did you get when you multiplied the fraction times 11.0093? Was it
I got. Say it again.
8.82 something?
Right.
So 8.82. What's the fourth digit?
It's. I think my calculator messed up. 818. It's 8.818.
8,
Yeah, so 18.
818. So let's do that. So 8.818. And that's plus. What did you get for the other number?
I got
1 point what?
1.99.
All right. So those two numbers combined will give you your average mass. And these types of problems, they're presented multiple ways. So we're going to look at another way of calculating that, because sometimes it'll give you the average mass and have you calculate the abundance. Sometimes it'll give you the abundance and have you calculate the average mass. So these problems can be presented more than one way. All right, any questions about that? So we just need those numbers, right? We need the fraction or the percent abundance, and we need the mass of the isotope. If we have those two numbers, we can calculate the average mass. And then if we have any two of them, we can calculate the third. All right. Any questions about that example? Anybody still writing that down? All right, let's look at another example. We're going to calculate the average mass of magnesium, and then we're going to do another example where we actually have to figure out the abundance, which is that's a little bit different, but we're going to do another example where we have to figure that out. So let's do another example. All right, so we have a magnesium sample. All right, and it's 24. So magnesium 24. And this is present in 78.70% natural abundance. You got magnesium 25. And this is present in 10.13% natural abundance. And then magnesium 26, which is present in where is it? What number? 11.17% natural abundance. Keep in mind, this anytime you have these fractions, they have to add to 100. So let's go ahead and make these into fractions. So this is 0.7870. This is 0.1013. and this is 0.1117. Everybody okay with that?
Yes.
So this is how we'll represent this. We'll call it, sometimes you'll see it represented in the book as fractional abundance. All right, it's the same as the percent abundance, but we're going to represent that as a fraction because we know we need that fraction in our calculation. All right. So now how do we calculate the average atomic mass? We know what the atomic mass is for each one of these, 24, 25, and 26. The number is actually more precise than that. So we're going to, we'll look at those numbers, those precise numbers to do the calculation. All right. So for magnesium 26, and we're going to do the average. It's going to be 0.1117 multiplied by 25.98. This is the actual, and this is in AMU. All right, it's going to be that plus, I'll do it this way, plus for magnesium, go ahead.
If I'm not mistaken, the 0.1117 times 25, would that be, oh wait, no, you said that's the exact number. Okay, never mind.
Yeah, it's the exact number. So the 26 that you see over top of it, that's that number rounded up to 26.
Got you.
Good question. All right, so then for the magnesium 25, the isotope, it will be 0.1013 times 24.99, which is the exact atomic mass of that isotope, AMU. And then it's going to be that plus 0.7870 times 23.98. And for a question like this, all those numbers will be given to you. The percentages as well as the exact atomic or isotopic masses have to be given. So it'll be this plus this, right? So this number plus this number plus this number would give us our average atomic mass. All right, anybody got those calculated?
The first one is 2.902.
Okay. And that's in AMU. Right?
Yes.
Keep our units straight. Shrink that down soon. Okay, what about the second one?
The second one is 2.531.
Okay. And the third one?
The third one is 18.87. Wait, yeah, 18.872.
All right, so when we add those three together, what do we get for the average mass? Because that's what it is, it's the sum of those three numbers.
I got 24.305.
All right, and this is in AMU. If you look at the periodic table, that's the number that's on the periodic table. It's actually, we're going to keep it in 4 sig fig, so it'll be 24.31. All right, If you look at the periodic table, that's the exact number that's there. So again, the atomic mass that's represented on the periodic table is the average of all the isotopes of that element that exists. All right. Anybody got any questions? We're gonna do one more example of this, and then we're gonna push past to a push through to another topic. All right. Any questions? Everybody good? Everybody on the boat? Nobody needs a life jacket yet. All right. Good. All right. So let's do one more example of atomic average atomic mass, but this time we're gonna solve for something else. We're gonna actually try to solve for the fractions. All right, because we're not going to be given the fractions. We're going to have to figure that out. So for our third example, let's talk about it. So example 3, and trust me, we'll do more of this in recitation as well. All right, so for example 3, let's look at it. So we have chlorine. So this is naturally occurring chlorine, and chlorine 35 has atomic number 17. So this is the naturally occurring chlorine. Spelling right. All right, naturally occurring chlorine has we see the atomic mass of 34.96. Zero 0.35. So when you see this right here, naturally occurring, right, that's telling you that this is the average, right? The number that you see for naturally occurring chlorine is the average. All right. So we have naturally occurring chlorine has an isotope 34.96035. And then we have another isotope, chlorine 37, which has a mass of 36.96590. All right, let me fix this too. This will be isotope 1. And then this is isotope 2. I'm gonna give you the average in a second. So fix that in your notes. So the average is 35.453. All right, so let's get this together. Average mass of chlorine is 35.453. That average mass comes from 2 isotopes. One is chlorine 35, the other is chlorine 37, right? And then so chlorine 35 is 34.960 and 35, and then chlorine 37 is 36.96590. So those two numbers are my fractions. Is that right? I'm sorry, those two numbers are my isotopic masses. What I need to know, the question is asking, what are the fractions? I'm just going to say abundances. Right, so we need to calculate the fractional abundance of each one. So that's what this question is asking us to do, calculate the fractional abundance of each isotope. All right, so we need to calculate that, but we don't know what the fraction, we don't know what they are. But what do we know about the fractions? Even if we don't know what they are, what do we know about them? Don't they have to add to 100?
Yes, they do.
They have to add to 100. So the way we approach a problem like this is if we know what the average mass is, then the isotope that's closest to that is going to be the higher, is going to have the higher abundance, right? And the isotope that's furthest away from that is going to have the lowest abundance. So what we're going to do is set this up so that we can calculate the fraction. So we're going to take the 36. So the average we know is 35.453. And we're going to set that equal to, in this case, is going to be 36.96590. And that's going to be times, we're going to say, and I'll explain this in a minute, times 1 minus x, right? If x is the total, I'm sorry, if 100 is the total, then x is the percentage or the fraction, is going to be a fraction of that, right? So that plus the other number that we used, 34, let me make sure I write the right number down, 34.96. That's what we have here, times x, right? So we're going to actually solve for x, right? We got to solve for x. X is going to be the fraction, and then 1 minus x, which would be 100 in this case, because they have to add to 100. The 1 minus x will give us the second fraction. So the first fraction is going to be x. Second fraction, 1 minus x. If we solve for x, we can just plug that into the other equation and subtract it out. All right. So let's do that. So let's take, this one has to be distributed up top. So we're going to take that and multiply it by that and by that. All right, so I'm going to write this out down here. So it's going to be 34.96035x plus 36.9, I'm sorry, yeah, I said 36, that's 34, 36.96590 minus 36.96590x. Yes or no? And this is going to be set equal to 35.453. Is that right?
Yes, it is.
Okay. When we distributed that top number, it's 36 times 1 and then 36 times x. So that's how we get these two terms right here. Now we need to just combine like terms. So we're going to take these two numbers with the x term and put them together. So somebody do that calculation real quick, that 34.96035, and subtract 36.96590 from that. Excuse me.
I got
Should be,
that's a 36.9, right?
yeah, 36.96590.
So I got negative 1.9999865.
Okay, we'll take that. All right, so, and that's x, right?
Mm-hmm.
So that's our X term now. And then this is going to be plus what? 36 point. 96550. And we're going to set that equal to 35.453. Everybody okay so far? So I have two terms. I have the X term. And then I have a numerical term. So now let's get the X term by itself. What do I need to do? This is all this is just, we just doing algebra now. So I'm going to subtract both sides. Is that right? That's going to
Yes.
cancel that term. And then this minus 36.96590. What do we get for that? It's going to be a negative number.
That's negative 1.5129.
Okay, so negative 1.5129. Perfect. So both numbers are negative, so we can actually just drop the negative signs on both sides, and it'll be 1.5129 equals 1.99986x. Are we okay with that?
Yes, sir.
So now we need to solve for x. Just divide both sides by this number. That's going to cancel. 1.99986. So what is x?
I got 0. It's a long number.
That's okay. Give me four sig figs.
Okay. 0.7565.
Okay, we'll keep that. All right. Are we everybody okay with that? So if that's x, then what is 1 minus x? So 1 minus 0.7565. We just plug that in, right? And what do we get for that?
0.2435.
2435. Perfect. So now these are our isotopic fractions. So this is the isotope fraction for the chlorine 35. And then this one is going to be the isotope fraction for the other isotope. All right, are we following that? Because we said that one was the 1 minus x, and then the x term was connected to the chlorine 35 isomer. All right, so what are the percentages now? I just take each number and multiply it by 100 to find out what the percent abundance is. So I'm gonna take this number right here and multiply it by 100. So that's going to be 75.65%. Is that right? And then over here, do the same thing. And it's going to be 24.35%. Right. So the chlorine 35 isotope, which is represented as 35 Cl17, not 71, exists in 75% natural abundance. And then the chlorine 37 exists in 24.35% natural abundance. Right. So sometimes, again, you can have the masses of the isotopes, but not know the fractions. So anytime you don't know the fractions, you have to set it up in a similar fashion where, depending on how many isotopes there are, that's going to determine how you set it up. If there are only 2 isotopes, one of them is going to be the mass times X, and one is going to be the mass times 1 minus X. All right, if there are 2 isotopes. If there's one isotope, if there are more than 2 isotopes, then you have to have some other information. We're going to work a problem like that on Thursday, as a matter of fact. All right, any questions about this? Go ahead. I see 2 hands that went up.
Can you hear me?
Mm-hmm.
Okay, so I swear every time I look away for like a second, all of a sudden we're doing math. So we're calculating what shelf life or just
No. Don't worry. We're not doing shelf life yet, or half-life. You're thinking about half-life.
yeah, that one.
That's several chapters away from here.
So we're doing
Natural abundance, percent abundance.
and that means
Hmm?
and that means
It means that if you were to dig up, let's say, chlorine is actually a gas, but let's say you collected a gas sample of chlorine, it will contain 75% of chlorine 35, and it would also contain 24% of chlorine 37. That's what that means,
okay,
based on what we just calculated.
right.
Mm-hmm.
And can I talk to you after class?
Yeah.
All right.
All right. That was a second hand that went up. Also, go ahead. All right. I think we'll wait. We'll wait and start the next section on Friday, because this is a lot and I want you to process it and I don't want to overwhelm you. So we'll wait and start the section on chemical formulas on Friday. Any other questions about anything?
Anything?
Sure.
Okay, so
Hold up, let me start recording now. We don't need everything on YouTube.